Hello everyone. This is a video I'm making on continuing the Hamiltonian equations of motion. Now, if you remember, we discussed uh, the Hamilton H function in the last video, but I made that a couple of weeks ago and I didn't get a chance to make any more videos. So I'm going to finish off the video for Hamilton equation of motion. Um, Actually, I think I'll have to do another video too to do examples, but anyway, so we're going to continue on the Hamilton equations of motion, and we're going to continue on our understanding of converting Lagrange equations of motion into Hamilton equations of motion. And so hopefully this is still, yeah, it's dry. Okay, so we're going off, so our purpose is, so let's do a review of the Hamilton H function. So the Hamilton H function was basically, so if you remember, we have a Lagrangian, which is kinetic energy minus potential energy. And if you're missing, so the main idea that we got, right, was that if you're missing a coordinate, one of the coordinates, QA, if it's missing, right, so there might be a QA dot, but not QA. And if it's missing, then this leads to a conservation principle. And that lends us to a conservation saying that partial of L with respect to QA dot is equal to a constant. It is a constant of the motion. So if you're missing a QA. So by similar analysis, right, so remember this whole idea, right, was this idea of symmetries in Lagrangian leading into modern physics, right, was M.A. Noether. So famous physicist slash mathematician slash scientist that basically she actually modern physics is based on her ideas of symmetry. Anyway, so but if it's missing QA, but if it's missing a T, there's no T in the Lagrangian, we get that the H function, which was defined to be the partial of QA dot QA minus L, and we're summing go from A is 1 to N. So I'll put parentheses here. So whatever this H function is, right, so this is called the H function, the Hamilton H function, not to be confused with the Hamiltonian. So this is called the H function. So remember, this function is a function of Q1's dots, Q2, dot, and time. So it's got the generalized coordinates and the derivatives of generalized coordinates and time. So this is not something called the Hamiltonian, which we're coming up to, but we know that if you're missing t, then this h function is conserved. It is a constant of the motion. So whatever this is, it's conserved. It's a constant. It doesn't change. And in the special case, if you know that the kinetic energy is really functions of q1 maybe to qn with no q dots, q1 dots derivative. So you have a second function of q1 to qn, maybe even time in here. So q2 dot squared plus dot all the way to the end. If your kinetic energy is in this form of quadratic terms in the derivatives of other coordinates of functions, right, then we know that the h function, right, becomes the total energy, T plus V. Only in this form, right, we get that V is the potential energy in terms of coordinates and time maybe, but T plus V is the total energy. So if you're missing T and your kinetic energy is in this form of quadratic terms of the derivatives of time, then we know that the H function is total energy. So that's what we've said in the last video, and hopefully I summarized it enough so that you can continue. So I now want to digress a little bit, right, to explain an idea of taking a second order differential equation and converting to first order differential equations, a system of differential equations. And I want to make sure you understand that idea by, let me erase this and construct a second order differential equation just to make sure you understand the idea. So when we talk about Lagrange equations of motion, right, actually I'll say it in a couple of minutes. So let me erase this first and let me do an example of something, of converting a second order differential equation into first order, a system of first order differential equations. sorry, I don't feel like editing the videos, so I'm just going to basically, you're going to have to watch me erase everything. Gives you time to think about things anyway, right? Contemplate. Okay, great. Hopefully this is dry. Okay. Great, back to video. Okay, so we know what the h function is, and with the h function, right? And so I'm going to digress slightly, right, and start with just a second order differential equation. For example, let's make it as, it's not dry yet. Hopefully, okay, let's do it over here again. Okay, let's do it over here. So here's a second order differential equation. I'll put some numbers in here. dx dt plus, that was a mistake. So nice simple homogeneous differential equation. So I'll just put x equals 0. And construct a characteristic equation. We know that we can solve this differential equation pretty straightforward. We can find the basis vectors. I have videos already set up on that, so you can watch those videos. But the main idea is this. Here's a second order differential equation. One second order differential equation. I want to convert this by doing a substitution and saying, let's construct a new variable, dx dt. Let's call it u. If I make this substitution in here, right, we'll see that this is now, the second derivative becomes a derivative of u plus 2u plus x is equal to 0. So you might say, well, so what? Now I have two equations, but two equations of first order. So we have two equations of first order. And to make this, why this is so important, so we have now two equations of first order. So taking a second order differential equation, we convert it into two equations of first order. Now I'm going to rearrange this, right, and see why this is so useful in doing theory. So if you can do theoretical analysis, first order differential equations are very good because we can actually use matrix operation to solve them. And this second order is kind of a little more difficult. But the two first orders, so take a look at the first equation. I'm going to rewrite this in terms of dx dt is equal to u. I'm going to take the second equation and say that this is du dt is equal to, I'll put the u first, I'll put the u, actually I'll put the x first. So it's minus x minus 2u. Yeah, and I'll put some spacing in here, okay, u. But if you kind of look at this carefully, right, you'll actually notice that I can actually convert this into a matrix equation of x's and u's. And so this would be 0, 1, minus 1, minus 2 of x's and u's. This is great because I now have basically an equation, right? A first order matrix equation. And if I kind of use like my Dirac notation that we use a lot in physics, right? So I can call this the ket, let's call it W, the ket W, and I'll call this the matrix A, and this is the ket W again, and this is the derivative over time. So we can have a general equation, and I can actually solve this equation right away. I can actually solve this equation in terms of matrix methods, right, and say that the full solution, right, is given by, I'll put the solution over here. So the full solution is W, which is a function of time, the ket, is given by a solution of EA to the T times W at 0, which is the initial condition. I have a full solution. I can expand this out, but the main idea I want to get across, right, is that we've taken a second-order differential equation into two first-order differential equations, and first-order differential equation like this, right, is very easy to solve. For example, this is the abstract solution. You might say, what is an exponential of a matrix? And that's actually, I'll have to make some more videos of this. I just didn't have time to, but anyway, the basic idea is that we can solve first-order differential equations. We can apply more abstract mathematics. We can actually use these ideas, right, to actually construct, abstract solutions, and we can actually evaluate these solutions. We can diagonalize the matrix A, and we can actually construct the solutions, which is actually solving a second order, but a little bit easier because we have matrices to solve. Matrix A, this term, 0, 1, minus 1, minus 2. Anyway, the key idea I want to walk away from here is that you can take a second order differential equation and convert it into two first order differential equations, 1 and 2. Here's two first order differential equations, a system of first order differential equations. Now, the Lagrange equations of motion we're going to see, basically the Lagrange equations of motion, we're going to see is that there are n generalized coordinates, so we're looking at n second order differential equations. If I do this idea of substitution, right, you'll actually see that the Hamiltonian equations of motion, which I'll just call it HEOM, Hamiltonian equations of motion, right, we'll get 2n first order differential equations. A system of 2n first order differential equations, which is great. And this Hamiltonian equation of motions are great because they can lend themselves into leading into, for example, they can go into quantum mechanics by, for example, canonical quantization methods, right? We can quantize the Hamiltonian into, quantum mechanics. We can actually use the Hamiltonian equation of motion to explain evolution of systems of particles. And that leads us into conservation of phase space density, which leads us into statistical mechanics. So there's a lot of beautiful ideas that we get from simply looking at 2n first order differential equations. So first order differential equations are great for mathematical analysis and playing with things in terms of theory. Second order differential equations are kind of complicated, and they're kind of work. You have to work with exponentials and characteristic equations, and very time consuming. But in quantum mechanics, we're always going to be working in first order differential equations. In time, anyway. First order in time. Schrodinger equation is first order in time, or condensed matter physics. Anyway, so it's a slight digression. Main idea, system of, if you have n second order differential equations, we can convert them into Hamilton's 2n first order differential equations. And this is an example. So let me erase this. Let me start from the top so that it dries up first. I'll just make sure that this is all dry. Okay, so our general idea now is, so you got the idea, we're taking a first derivative and creating a new variable out of it. And so now we're going to start off so this is the Hamilton equation of motion, but we're going to start with the h function. So our h function, right, was basically the sum taken of 1 to the n variables. Remember how we constructed this? We constructed it by noticing that a missing t lends itself to a conservation, and we get this function. And this function, right, happens to be energy in special cases when the kinetic energy has a certain form of quadratic terms in the derivatives of time of the generalized coordinate variables. Anyway, so this is the partial of L with respect to QA dot minus L. So we're going to make a substitution, and the substitution, right, is that we want to take derivatives and associate it with a new variable. This new variable is going to be called the conjugate momentum. Conjugate momentum. And we're going to call this PA associated with the variable QA, and it's going to be equal to partial of L with respect to QA dot. So what you're saying is that if somebody gives you a variable like Q1, we get a conjugate momentum P1. And these are all conjugate variables, so P1 and Q1 are called conjugate pairs. Conjugate pair. So this is momentum and this is position. So this is the conjugate momentum variable and this is the conjugate position variable. So remember, this is generalized coordinates. Okay, so I think I should do examples on this to make sure we understand this. So let's start off with the h function. So let me do some examples on this to give you an idea what's happening. So here's an example. And we'll do a simple spring system. Spring system was Lagrangian. So here's my spring system. It's frictionless surface, spring constant is K, attached to a mass M, equilibrium, displacement, let's call it Q. So from equilibrium, we pull the mass, and by displacement Q, we want to find the equation of motion. Lagrangian tells us T minus V. So the kinetic energy happens to be 1/2 mass times Q dot squared, the velocity squared, minus the potential energy associated with the spring, which is 1/2 Q squared. Yeah. So let's convert the h function in terms of, so let's calculate, there's only one coordinate variable, right, Q, and so the conjugate momentum happens to be P is equal to the partial of L with respect to Q, and this is MQ dot. So this is from the definition, so this is the definition, DEF. So this means that Q dot is equal to P over M. Okay, great. So let's look at the h function. The h function, right, is really functions of Q1 to Qn and time. It might include time. But I'm going to make a substitution. Oh, sorry, I made a mistake. It's a function of Q1 to Qn, but it's also a function of Q dots. So Q1 dot, Qn dot, and time. The h function in this case happens to be equal to the partial of L with respect to Q dot, which is MQ dot. So this is really MQ dot times Q dot. The first term is only one term, minus the Lagrangian, which happens to be 1/2 M Q dot squared minus 1/2 K Q squared. And if you stop and think a little bit, right, do you notice that this Lagrangian, right, the kinetic energy term, right, happens to be in the quadratic in the derivatives of time? Like this is a quadratic term, so therefore, whatever this is, right, is the h function is going to be equal to the total energy of the system. We also notice that there's no t in here, right? Because there's no t, that energy must be, h function is conserved. So we're saying the total energy is conserved in this equation, in this, well, this. So we substitute this in here, and you'll see that minus gives you 1/2 M Q dot squared plus 1/2 K q squared. Lost it there. So it happens to be total energy in the system. So this is the h function. Now what we said about substitution, let's do that substitution. So when you have a h function which consisting of q1s to q and t, right? When we make a substitution of q dots and solve it in terms of p's and q's, that leads us to a new function called the Hamiltonian. That's our idea. So if we make a substitution of q's dots into p's, we have a new h function with p's and q's, and that h function, right, is called the Hamiltonian. The Hamiltonian. So I have to erase something. So erase this. We already know what q dot is, pm, so let's take a look at the h function again. So every time I see a q dot, I'm going to replace it with this equation. So this is now 1/2 m. So I'm going to call this a new function called h, and this is called the Hamiltonian. Sometimes just Hamiltonian h function, capital H, as opposed to the lowercase h, but this is the Hamiltonian. So sometimes people just say the Hamiltonian. So the Hamiltonian is equal to p over m squared plus 1/2 k q squared. And what's really interesting with the Hamiltonian, right, is that this is a functions of p's and q's and time. There is no q1, q dot, and that's why I was using a lowercase h, right, and called it the Hamiltonian h function. So remember, the lowercase h, right, is a functions of q's and q dots and time, while the capital H, right, consists of p's and q's. These coordinates, right, of p's and q's is sometimes referred to as phase space, and I'll explain that, I guess, how much time, 22. I'll probably make another video of it because there's a big discussion we have to go over in terms of conservation of phase space and motion in phase space and what's happening to systems of particles in phase space. And what does it mean when we have to get the derivation of the Hamilton equation of motion? But this is called the h function. So the procedure is pretty straightforward. So we take our Lagrangian, get the conjugate meant to associate with each of the variables, solve for the derivatives, back substitute into the h function, and we'll get the Hamiltonian. So this is the Hamiltonian, our first part of our Hamiltonian equations of motion. So let me erase this and do another example. And the next example, I think I'll make up a Lagrangian, something arbitrary, so you understand that you can't just guess these Hamiltonians. The Hamiltonian, the capital H function, right? It's a mechanical construction. You always start from a Lagrangian. Okay, great. So let's do another example. And here I'm going to construct the h function, the Hamiltonian. I'm going to construct the Hamiltonian. So maybe I'll just say, find the Hamiltonian I'm getting absent-minded. So if somebody gives you a Lagrangian, and let's make it up. So let's say it's Q1 dot squared plus Q2 dot squared minus Q, I don't know, 1 cubed. Made that up. Anyway, so a couple of things. What can you say by symmetries, right? We know a couple of things. We know that what's being conserved. Notice that Q2 is missing in this equation. So we know that the partial of L, we know that the partial of L with respect to Q2 dot is a constant. In this case, it happens to be 2 Q2 dot. So whatever that is, it's conserved during the motion because Q2 is a cyclic variable. We also notice T is missing, so we know that the H function is being conserved. And for me to calculate the H function, let's write it out. So the H function is going to be equal to the sum of the partials of L, QA dot minus L, taken from 1 to n. In this case, it happens to be the partial of L with respect to Q1. So that would be 2Q1 Q1 dot, actually, Q2, the partial of, yeah, and Q1 dot plus the partial of L with respect to Q2. So that would be the 2Q2 dot multiplied by Q2 dot minus the Lagrangian, which is Q1 dot squared plus Q2 squared minus Q1 cubed. Okay, so your H function then becomes minus that, so it's really Q1 dot squared plus Q2 dot squared minus minus becomes positive, so this is Q1 cubed. We know what this is. It is the total energy of the system because we know that the kinetic energy term, right, is in this form of quadratic terms and Q1s, Q2s, and so on, right? So we know that this is the total energy of the system. We know that it is conserved because there's no T, there's a missing T. So you're saying the total energy of the system is being conserved. But now I want to construct the Hamiltonian. And the Hamiltonian is basically, we're going to rewrite this in terms of Q1s, Q's, and P's, conjugate momentum. Now to find the conjugate momentum, right, we have to say that P at 1 is the partial of L with respect to Q1. In this case, right, it happens to be 2Q1 dot. So if you solve for Q1 dot, you'll find that that's P1 over 2Q1. Similarly, the conjugate momentum 2 of the conjugate variable Q2 is equal to the partial of L with respect to Q2. And that's equal to, looking at the Lagrangian again, it's 2Q2 dot, which means that Q2 dot is equal to P2 over 2Q2. So we can write the Hamiltonian. It's basically the H function with the substitutions of P's and Q's, and so the Hamiltonian H, this is the Hamiltonian, is really Q1 times Q1 dot, which is P1 over 2Q1 squared plus Q2. Q2 dot is basically dusty down here, the basement. And then there's a Q1 cubed. I won't bother reducing it. There's nothing special about doing this reduction anyway, but this is the Hamiltonian H. So this is the Hamiltonian. Hamiltonian, capital H. So please don't get confused with the lowercase h, which is the Hamiltonian h function, right? The lowercase h function, right, consists of generalized coordinates and their derivatives and time. In the Hamiltonian, right, that we're going to use for the Hamiltonian equations of motion, right, it's going to be consisting of phase-space variables, Q1s, P1s, Q2s, P2s, and so on, right, all the way to including time. Anyway, so hopefully these are two examples. Now, since it's already 30 minutes, so let me derive the Hamiltonian equations of motion. So remember, we want to work with Hamiltonian equations of motion because they lend themselves into doing theoretical analysis that leads into things like, for example, quantum mechanics, also to statistical mechanics and ideas, and anyway, for theoretical ideas. Okay. Okay. Now, so let's go back into how we are going to derive the Hamiltonian equations of motion. So the idea is that originally, right, our Lagrange equations of motion, which was written as d dt partial of L qa dot minus partial of L with respect to qa is equal to 0. So this is the Lagrange equations of motion. We had n of these equations, and we want to convert this into Hamilton equations of motion. And this was derived originally, right, in terms of, well, actually Goldstein's textbook, right, is the greatest text in their derivations. So you should take a look at Goldstein. But this derivation lends itself, right, into saying that we can actually, this equation can be derived as a functional. So if we have something called the action, right, of a particle going from point A, or at time ta, to a point tb, and L dt. So imagine that you have a particle in taking one of the coordinates, for example, q at A, and this is time. So at point A, here's the particle. The particle appears over here, so it takes some arbitrary path, gamma, across this path. And if you remember, right, in one of the videos prior, we discussed variational calculus, right? We said that the variation of A, when it's set equal to 0, right, it derives the equations of motion, Lagrange equations of motion. So a lot of textbooks, right, they decided that instead of Lagrange equation of motion starting from here, right, a much simpler idea is that we say that we have an action which takes the Lagrangian L, which is kinetic energy minus potential energy, over some two different times, t at A and t at B, and takes some gamma path, right? And the variation of A, setting the variation of A equals to 0, using variational calculus, right, leads us to the Lagrange equations of motion. We're going to do exactly the same thing. I take the variation of A, but instead of using coordinates, right, of Q's and Q dots, we're going to be changing it into Q's and P's. And so we can take the same equation and doing the variational calculus, right? But this L, right, will be rewritten in terms of P's and Q's instead of Q's and Q dots. And this leads us into Hamilton equations of motion. And so, yeah. And where we're going to start, right, is take a look at the H function. So our H function was written as, oops, partial of L with respect to Q at A dot, Q at A dot minus the Lagrangian. This is our H function. I'm going to basically solve this equation for L. And we're going to do a substitution. Remember, partial of L with respect to K is the conjugate momentum associated with the QA coordinate. So we'll get that. So if I make that substitution, this becomes the Hamiltonian H function. But of course, so the Lagrangian can be written as, so this is P at A, so A taken from 1 to n coordinates of PA QA dot minus the Hamiltonian. And this is where I'm going to do the variation. So I'm going to substitute. So the Lagrangian is written in terms of coordinates of P's, A's, and QA's. And I know there's a QA dot, it doesn't look right, but we'll actually see when we do the variation it disappears. And of course, H is a function of P's, Q's, and time. Okay, so that's where I'm going to start. And so let me erase everything and let me try to get a clean board, because this might be I might need some extra space. Okay, so our action variable, our action, right, is basically it's a functional, right, that takes the integral taken from t points ta to tb of the Lagrangian, but now the Lagrangian can be written in terms of the Hamiltonian. So we can say this is really the sum 1 to n of P at A times QA dot minus the Hamiltonian dt. And I'm going to do the variation of this instead of equal to 0. So we can take the variation, and so the variation of this whole symbol, right, which is basically, I'm going to pull out the symbol and just rewrite this and saying that this is really A from 1 to n of the variation of P at A QA dot dt. And the variation of sum is sum of the variation, so here's our summation, and then this is the integral of the variation of H Actually, you know what? I think I'll just write in one line, so try to make it separate and try to. I'll skip some steps because this is just. It's in the notes actually. It's in my notes. So the exact lower level steps. So this is the variation, and of course, yeah, I guess I'm going to have to because this is not done yet. So never mind. Okay, so I guess I'm going to keep this. And so this is the variation of h, and I've moved up the intervals. So this is really TA, TB. Hopefully you know all this, right? I don't want to keep writing these symbols down. So first note, what is the variation of h? Well, that's partial of h with respect to PA, variation of PA, plus the partial of h with respect to QA, variation of QA, sum from 1 to n, sum from 1 to n. There's no time because remember, we're looking at functions of time. So time is our independent variable. So variation only changes in terms of p's and q's. So you should take a look at the video that's already done on variational calculus to review these variation methods. Okay, so we can substitute this into here, and notice the summation from 1 to n and the 1 to n, so I can pull out the whole thing and we're left with 1 to n of an integral taken from TA to TB of the variation of PA QA dot minus the partial of h with respect to PA minus partial of h with respect to QA and dt. Okay, so I pulled out a is equal to 1 to n. Now the variation, right, if you kind of look at this carefully, right, actually, let me take a look at this one integral. Maybe I'll just do it in your head. So the variation of this, right, is going to be equal to QA dot variation of PA. So this is your, product rule, plus the P at A variation of Q dot at A. Okay, so these are the terms. So I don't feel like rewriting this, but I guess I'll have to. So I'll simplify this and say this is really Q dot A variation of P at A plus. Now the variation of a derivative is the derivative of the variation, so this is really P at A variation of Q at A. So remember, you'll have to look over the videos on your variational calculus just to make sure you know these steps, what they mean, and so I've put that in, and then there's the minus partial of h with respect to P at A, variation of P at A, minus the partial of h with respect to Q at A, variation of Q at A, dt. Okay, now notice the dt, and then you're looking at basically a integration by parts, something dq, d variation to q. So if you take this term, right, and I'll put it over here, this term right here, right, becomes, by using integration by parts, right, by dt and integrating, right, you'll actually see that this becomes a dpa, and then you'll get this as the PA variation of QA minus variation of QA dPA. So when you integrate this, this integral, right, you'll notice that this term, right, because the variation at the endpoints, right, is 0. So you're integrating 1, right? And so this becomes 0. And so you're left with the final equation rewritten TA to TB of, and I'm going to rearrange these terms. So there's PA, there's a PA over here, so that becomes QA dot minus partial of H with respect to PA, variation of PA. Okay, so this term, finished. And this term is actually this, so we have plus and dPA dt, so this is really divided by dt, multiplied by dt cuts you back into here, so this becomes PA dot minus the partial of H with respect to Q at A, variation of QA, and dt. And so we're left with this, and we're finished. So basically, for this variation, this is the variation of A. So if you notice carefully, right, that the variation of A, right, is set equal to 0, which means that all variations, right, the only way for this integral to be 0 is that the variations of PA and QA, these two terms are equal to 0. So this leads us to, the summation is meaningless, but so which means that QA dot minus partial of H with respect to PA is equal to 0, and PA dot minus the partial of H with respect to QA is equal to 0. Oh, I think I made a mistake here. There's an extra minus here. Sorry, there's a minus here. I forgot the minus. The minus comes from here, here. This is the minus. The minus going dPA dt. Sorry, let me write it down. And these two equations are called the Hamilton equations of motion. So kind of, yeah, you have to start getting used to this mathematics, especially if you're in physics. It's anyway, since all of you are in physics, right? Anyway, I'm going to rewrite those over here on top and summarize what I've done. And how many minutes? 48. Oh, it's long. Oh, yeah. The examples I'll do, I guess, next video on phase space. But actually, maybe, yeah, maybe I'll do one example. Like, so. Okay, so I'm going to move all the terms to one side and the derivatives on the other side. Alright, so we can now summarize the equations of motion, and I think I'll do one example before we call it quits on this video. And then I guess another day I'll do some more examples and then discuss phase space. So the idea is that the Lagrange equations of motion were the Hamiltonian. Let me summarize. So the Hamilton equations of motion is it's long. It's not easy to construct the Hamiltonian, but once you have the Hamiltonian, we know that Q at A dot, the derivative of the Q at A, is given by the partial of H, the Hamiltonian, with respect to P at A. But PA dot, the derivative of the conjugate momentum, is given by the negative of the Hamiltonian with respect to Q at A dot. Together, these two are called the Hamilton equations of motion. So let's do an example of this, a quickie. So if you remember in earlier, right, we already discussed that the Hamiltonian, right, for the spring system, right, was given by 1/2 p squared over 2m. We derived this plus 1/2 k, I think I used q, right, so q squared. So here's our Hamiltonian. That it took us a while to derive this Hamiltonian because we had to find the conjugate momenta, and once we did this, we had to construct the h function, the Hamiltonian h function, and from the Hamiltonian h function, we then construct the Hamiltonian h, capital H function. And once we have, then we have the equations of motion. There's only one conjugate variable, so we just have to solve for one. So this is really Q dot is equal to the partial of H with respect to P, which in this case happens to be P over M. So the first equation is this. The second equation says that P at A happens to be P dot is equal to the minus of the partial of H with respect to Q. In this case, it happens to be KQ. So together, right, these are the two equations of motion. And if you're wondering, right, it doesn't really give us anything new. Lagrange equations of motion are still the easiest way of solving this problem, but for theoretical analysis, right, these equations are useful. And if you're wondering, are they the same, right? And we actually take a derivative of double derivatives and reduce this to one variable and say the second derivative is given by minus kq dot. In this case, it happens to be minus k p over m. So second derivative is equal to minus k over m times p. So we can solve this equation. So there's a periodicity in the momentum of the system, and we can do it the other way around. I can take derivative of this, right, and say that this is really q double dot is equal to p dot over m. P dot happens to be minus k, so this is really minus k over m q. We have a second solution. We can solve for q. It's a second order differential equation. So actually it's very painful to do it this way, but the main reason we're doing this, right, is that these Hamilton equations of motion, right, leads into more advanced ideas in statistical mechanics, quantum mechanics, and more advanced physics ideas. Okay, so here's an example. So time cumbersome, but these are the equations of motion. You should memorize them, just like the Lagrange equations of motion. You should memorize them. They're difficult to get to, but memorize them. Anyway, that's it for today.